Here we're going to talk about the hybridization in molecules containing multiple bonds, and lastly, kind of a synopsis of the bonding theories that we've talked about so far. So we have some hybridization in a molecule that now has a double bond in this situation. So here we have two carbons that have a double bond between them. This is just one of the carbons. It's actually both of them, but let's just look at one of the carbons at a time. So here would be this first carbon in this situation. Like we've seen before, let's promote those electrons to get them all unpaired. We're going to do a hybridization here. If you look at the molecular geometry around this carbon, this would be trigonal planar. This one is also trigonal planar, just looking at that local geometry. There's no lone pairs, just three bonding domains for each. So if it's trigonal planar, that means we have an sp2 hybridized carbon. So we're going to take this s and these two p's, hybridize them to sp2. But again, we're going to have this p orbital that's left untouched currently. That can still undergo chemical bonding. So that's an important feature here. This is the bonding that we've dealt with so far, but we're going to find that this unhybridized p orbital that was left alone, that didn't undergo that hybridization, will be what is responsible for double bonds and triple bonds. Okay, so here we have the hybridization like we had talked about, where we're forming we're undergoing the hybridization to form these sp2 orbitals. And I'm showing that for both of these carbons. And there's going to be an orbital overlap here that's directly between the two carbons. Anytime you have a bond that is directly between two atoms, that is called a sigma bond. All single bonds are sigma bonds. So this is how you would write that, a sigma bond. And it's important because that takes up the physical space directly between the two atoms. So here's a carbon, there's the carbon. The orbital overlap is happening directly between the two atoms. This is what we've seen the entire time. We haven't seen a different scenario. There is a different scenario, and that is called pi bonds. And this is what's needed for a double bond or a triple bond to occur. So here, this is the entire molecule. You're seeing that these sp2 hybridized orbitals are interacting with the 1s orbital of the hydrogens on both of these. And then we have the sp2 orbitals that are overlapping between the two carbons. Remember, there was that p orbital that was left unhybridized. Here's that p orbital that was left unhybridized for this carbon, and the p orbital that was left unhybridized for this carbon. Remember, on that prior slide, both of them had one unpaired electron in those. So actually, right now, it doesn't look like they're overlapping at all. Realistically, these are a little bit closer. This is dramatized just a little bit, but they can overlap. So here we're drawing those p orbitals once again, but just a little bit larger. And you can see that there actually is some orbital overlap that can occur with those p orbitals. It is occurring both above and below this other single bond, this sigma bond that was occurring. Since that's already taking up the space directly between the two carbons, multiple bonds need to occur either above and below that, or what we'll find is to the left and to the right of that. So this is kind of depicted as above and below. And that is the interaction that we call the pi bonding interaction. So it still is just two electrons that are being shared, but it's being shared in kind of two locations. It doesn't mean that there's two electrons here and two electrons here. It means this entire system has just two electrons, just like this whole system right here had two electrons. So this is called a pi bonding interaction. Again, a p orbital is forming a pi bonding interaction. A sigma bond is a single bond. So every single atom that we've dealt with so far has at least one, or every single bond that we've dealt with so far has had at least one sigma bond. Well, it can only have exactly one sigma bond. But we will never have just one pi bond and no sigma bonds. So all of the single bonding interactions you've ever seen have been the sigma bonding interaction. It might be between two hybridized orbitals or a hybridized orbital and an atomic orbital like we're seeing in this situation. But this has some unique features associated with this pi bonding interaction. So that is the second bond of this double bond. We can have multiple pi bonding interactions, however. This one is above and below, and like I'll show later, you could have one kind of out front here and out back, kind of taking up a different physical location. But this has some unique characteristics that are pretty distinct from a sigma bond that we'll talk about here. One of them is that sigma bonds can undergo rotation. So here, let's say if I were to rotate this one of these atoms with respect to the other. So here I'm rotating it 120 degrees this way. So see this chlorine is swinging down here, and then it's swinging even over to the left. As we're spinning this, the orbital overlap stays exactly the same as time goes on. So as you spin that, there's the same amount of orbital overlap. So it's actually totally okay and very common for sigma bonds to undergo this free rotation like we're seeing. As long as that orbital overlap stays the same, it's totally fine for us to do that. One of the consequences of a pi bonding interaction now, however, is that you can no longer have that rotation. When you think about this pi bonding interaction that you're observing here and here, that pi bonding interaction, in order for that to maintain that orbital overlap, you cannot rotate it at all. If you were to rotate one of those carbons, let's say 90 degrees one direction, these lobes would no longer be interacting in the way in which we had previously defined them to be interacting. So you cannot undergo bond rotation like that. So what it means is that this molecule here is distinct from this molecule. Here the chlorine is on this side and this side, where here they're on the same side. You cannot interconvert between these two molecules. These are two distinct molecules. These are structural isomers, like we had mentioned previously. Where these are all identical molecules, we're just spinning the single bond in these locations, and it's totally fine for us to do that. So this is one consequence of pi bonding interactions in a molecule. So again, remember it's originating from that empty p orbital. Okay, so let's try one of these just in terms of counting the number of sigma bonds and pi bonds. This is, again, remember this is the structural representation of a molecule. Each vertice, if it's not labeled, is a carbon. Okay, so let's determine the number of carbon-carbon sigma bonds and the total number of pi bonds in thalidomide. So this is thalidomide. It has an interesting history. It was used for treating nausea in pregnant women, and it actually led to a bunch of birth defects because of an unknown characteristic. And this dealt with actually something associated with the geometry. There was a geometry issue right here that you would learn about in organic chemistry that they thought wasn't going to matter, and it turned out to matter quite a bit. So this has an interesting history to it from a ways back. But okay, so let's first deal with the pi bonds. Remember, everything has one sigma bond. Anything beyond the single sigma bond is a pi bond. So here there is one of these two is a pi bond, pi bond, pi bond, pi bond, pi bond, pi bond, pi bond. Okay, so there are 7 total pi bonds here. Now let's look at the number of carbon-carbon sigma bonds. So here's a carbon and here's a carbon. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so there are 12 sigma bonds for those carbons. Again, remember, one of these bonds is a sigma bond, one of them is a pi bond. It doesn't matter which one, it's arbitrary, but you have a sigma bond and a pi bond. Here is a sigma bond and a pi bond, sigma bond, pi bond. Okay, so this is how we would count up the number of sigma bonds and pi bonds in a particular molecule. Again, there's a bunch of other sigma bonds here, like a sigma bond between this carbon and nitrogen that we didn't count, for example. Okay. All right, so here's an example. Again, in looking at these multiple bond situations where we have a sigma bond that can form, where let's hybridize the two to form an sp hybridization. So here's this molecule with a triple bond now. So now we have 2 p orbitals that are left unhybridized. So we have this this orbital and this orbital. They both can undergo chemical bonding once again. So what we're going to have is we're going to have the same sort of pi bonding interaction we saw above and below the molecule, but also to the left and to the right. So that's why you get this sort of system where you have a pi bond that's encompassing above and below, and a second pi bond that's to the left and to the right. So a triple bond is a single sigma bond, like we're seeing here, plus 2 pi bonds. Okay, so anything beyond a single bond is going to be a pi bond for our purposes. There are other sorts of bonding that can occur that we're not going to talk about. Sigma and pi are the first two. The next one is delta bonding, but we will not be dealing with that. Once you go beyond a triple bond, you would have to start dealing with that. For most things, we don't need to worry about anything beyond a triple bond. Triple bond is about as high as it goes for relatively normal molecules. All right. So let's use some hybridization to explain the bonding in formaldehyde. So let's take a look at that central carbon. Its geometry is trigonal planar. So that means it should have an sp2 hybridization associated with it. There's a roughly 120 degree bond angles. But remember that the hydrogen-carbon-hydrogen bond angle should be a little bit smaller, maybe 116 degrees, because that carbon double bond oxygen takes up a little bit more space. And that carbon-hydrogen bond, this is between the carbon's sp2 hybrid orbital and the 1s orbital from the hydrogen. This is the same, and these are both sigma bonds. Now between this carbon and this oxygen, however, this carbon and this oxygen, what we're going to say is this carbon has an sp2 hybrid orbital that's undergoing a sigma bonding interaction with this oxygen's atomic orbital. And likewise, this carbon has an unhybridized p orbital that will be forming the pi bond with this oxygen. Okay? For both of these situations, we can assume that this oxygen is non-hybridized. Though sometimes you might see it being shown as a hybridized orbital. It's okay to just represent these as p orbitals, for example here. It'd be fine for you to just say it's the oxygen's p atomic orbital. But that would be the sort of interaction that we're occurring. Okay, the hybridized orbital from carbon is the sigma bonding interaction, where the open p orbital of carbon is undergoing that pi bonding interaction. All right, so here are the bonding theories and how we can describe molecules with this sort of delocalized bonding theory. So we have Lewis theory, which was the Lewis dot structures. We have Vesper theory, valence shell electron pair repulsion model. Then we talked about valence bond theory, and then kind of a caveat beyond valence bond theory, which was the hybridization of atomic orbitals. Okay, so for Lewis theory, some strengths are that it gives us some sort of prediction about bond strength and bond lengths. Right? If there was a single bond, we knew that that was longer and weaker than a double bond, and a triple bond being even stronger and even shorter than a double bond, right? And they are pretty easy to draw, and they're widely used by chemists. It's a very common starting point, and you need very little information to start it. You just need to know the number of valence electrons in your system and a few basic rules about how to construct it. So this Lewis dot structures and Lewis theory are really helpful in that regard. It's a model, so it's not perfect, but it does have its uses. Okay, so some weaknesses with this is it's only two-dimensional, where we know that molecules are three-dimensional. So it does not give us an indication of geometry. It also fails to account for differences in bonds in compounds like H2F2 and HF. It just shows a single bond between those different molecules, where it's not really dealing with anything else like polarity or those sorts of features of a molecule. And it really doesn't do anything to describe why bonds are forming. It's just kind of that we can represent these as single bonds, double bonds, triple bonds, that sort of thing. Okay, so we can take it a step further and start to deal with geometries. So valence shell electron pair repulsion. It really helps us predict the shape of these molecules or polyatomic ions, and that's its main strength here. It's the first time we've accurately been able to describe the geometries of what's been occurring, right? Weakness, again, it's not going to explain anything about the why bonds are forming. It's showing kind of why, maybe giving you some justification for why the geometries are there, but that's about it, right? So valence bond theory is when we actually start to describe the formation of a covalent bond. It's an overlap of atomic orbitals, and these bonds are forming. They result in a molecule that has lower potential energy than the original isolated atoms, which starts to describe why a chemical bond would occur in the first place. So this is the first description of why we're observing this. It still has plenty of weaknesses though. So some of those, it fails to explain bonding in many molecules, in which the central atom in its ground state does not have enough unpaired electrons to form the observed number of bonds. So that is a major problem. So we vaguely said, okay, well, we're gonna excite that atom to get unpaired electrons, and then we can move forward. Another big weakness with valence bond theory is if you were just to talk about the atomic orbitals overlapping, this would now no longer justify the geometry once again. So it's almost like a backtrack in that regard, where valence shell electron pair repulsion model did show us the geometry, but once we start describing why the bond's occurring with valence bond theory, we lose sight of the geometry once again. And that's where the hybridization of atomic orbitals came into play that could help us then justify the geometry once again. Hybridization of atomic orbitals is not a separate bonding theory. Really, it's just the extension of valence bond theory. So it's saying, okay, well, the atomic orbitals didn't do a great job of doing the geometry. So instead, we're going to say that it's not just atomic orbitals, but rather it could be hybridized atomic orbitals. And we can actually start to then understand some of these bonding geometries and have some more indication of the different geometries that we would expect, along with the why it's occurring in some of these molecules. It still has some pretty major weaknesses. It does fail to predict some important properties of molecules. Some of them we haven't really talked about just yet, but it doesn't do a good job of predicting number of unpaired electrons in these sorts of systems. It doesn't do a good job of dealing with magnetic properties, for example. There's a bunch of things that it still doesn't do a great job with. It is just a model, but there are bonding theories that go beyond Lewis, Vesper, valence bond theory, and hybridization. The one that is the predominant theory that does the best job describing all of this is molecular orbital theory. And so here we've talked about atomic orbitals. There's kind of a next level, which is molecular orbitals, which we won't really talk about here. There is a little bit of talking about it in the book, but this is definitely a topic for future courses, but it all builds on this foundation. These are still very useful models and can give us lots of information about the molecule, though with a little bit more complex understanding, you can get even more of these physical and chemical properties ironed out with a more advanced model like molecular orbital theory. But these are kind of the theories that we've been dealing with so far, and they all have their different uses. They're all somewhat separate, but they also do play off each other fairly frequently. So Lewis theory, even though it's the simplest, it's still also the most commonly used. If you're moving on to organic chemistry ever, Lewis dot structures happen all the time. You deal with them continuously. Dealing with chemical reactions, you care about the hybridization of a carbon atom very frequently for organic chemistry. So these theories definitely don't go anywhere. They are still used and an integral part to a chemist's toolbox. So these are the brief overview of what we've learned about so far in this chapter.